Hello, IB Physics. Today we're going to start talking about stellar evolution, thinking about what happens to a star during its lifetime, and really getting into the different processes behind it. It is one of my favorite topics in astrophysics. But before we get into the stellar evolution aspect, I want to talk about what makes something a star. So we've learned about nuclear fusion and fission, but fusion is what is important for stars. And that is where we take smaller hydrogen atoms and smash them together to make helium atoms eventually. And this happens in the core of a star. And as that's happening, the fusion is producing lots and lots of photons, and those photons actually transfer into thermal energy. They hit different particles, so they hit hydrogen atoms and electrons and helium atoms, and they cause them to have higher temperature, higher average kinetic energy, because that's temperature. And these photons gradually make their way outwards in the star. And they don't do this in a linear fashion. As you can imagine, these arrows sort of imply it's linear, but the photons are bouncing around, hitting atoms, hitting electrons, and they're bouncing around here in the star's core, and then in this thing called the radiative region. And they actually go through something called a random walk, which is a math thing that you can get into in upper level math. But the thing that's really interesting about this is that the reason a star is able to remain a star and be stable and has actually a specific size is through the stability that's caused, that is the equilibrium caused by the hydrogen fusion happening in the star's core that's pushing outwards. So you can see these arrows are pushing outwards. And then all of the star's mass has a cumulative gravitational pull inwards towards the center of the star's mass. So towards the center of the star. So you can imagine it as this fusion radiation pressure outwards and gravitational force inwards from all of the star's mass pulling it inwards. And the star's size is actually determined by the balance between these. And so this is just a really useful thing to remember, that this is a radiation pressure from fusion within the star caused by the weak and strong electromagnetic forces pushing outwards, and that gravitational pull inwards. And we have a stable star only when those two forces are balanced. So our sun currently has a stable radiation pressure and gravitational balance. And so that means that it's stable, it's showing out the way it is. And this is something that's actually going to be really influential in what happens to a star over its lifetime. So you checked out Star in a Box already. You saw some really excellent observations about how the mass influences a star's fate, about what happens to the star's path as it travels, and what happens over time. So you've shared this, we've gone through it, and you've noticed that the mass of a star is really, really important. So less than 8 to 10 solar masses is going to be something kind of like our sun, and we'll get into the path of exactly what is happening here. From 10 to about 30 solar masses, we have what's sort of a large star, and this is something that's going to become a supergiant instead of a red giant. And again, we'll get into that a little bit more. And then when we have a star that's over 30 solar masses, that is an extremely large star, or a giant star. And we'll get into that as well. But the thing that I want you to really notice here is that the mass really matters. So the starting mass of the star has a really big influence in what its fate is going to be. Astronomers like to remember this: weight makes fate is a nice little way to remember that. But we're going to go ahead and start off. All stars start out the exact same. And they start out in a little stellar nursery where they are formed from gas and dust in that nebula. So this is a nice stellar nebula where we have gas and dust that are gravitationally coalescing. They're collecting together. And gradually we start getting enough pressure and temperature to build up, and the star starts to fuse hydrogen. It starts to ignite. It becomes a real star. When stars are just starting to coalesce and gravitationally attract together and building up that pressure and temperature, as the gases and dusts are compressed together due to those gravitational forces, we get a protostar, which is a star that is hot, but not yet in nuclear fusion, not yet fusing hydrogen into helium. Here's an actual picture of a protostar becoming a real star. So it's giving off thermal energy here. We can see the light, and here we're getting some potentially visible energy. There may be still visible energy, but it's pretty cool to see that this is something that we can actually look at changes happening in a nebula in an amount of time that like you can actually measure in our lifetime and see changes in our lifetime. Because most stellar changes don't really happen in human lifetimes. There's just a couple that we can actually see over a human's lifetime. So once a star becomes a real star, it becomes sort of a middle-aged star. Protostars are like maybe teenage stars, still rocky. Middle-aged stars are stars that are now stable and are in the main sequence. So they've reached that equilibrium between the radiation pressure outwards and that gravitational pull inwards, and they're happily fusing hydrogen. Okay, stars don't have feelings, but go with it. Fusing hydrogen into helium, and the process, as you can imagine, is actually a lot more complicated than, just hydrogen to two hydrogen atoms become one helium atom, because as you know, a helium atom actually has 4 baryons in its nucleus, and so we actually have to have 4 hydrogen atoms to start out with to get 1 helium atom in the end. And it goes through a pretty complicated process where we have some neutrinos and electrons and photons. Anyways, but these are most of the stars that you see in the sky. Most of the stars you see in the sky are in the main sequence. They're just living their normal star lives. And as you noticed on the star in a box, the smaller stars down here on the HR diagram that are cooler stars actually live way longer than the big, heavy, massive stars. So weight equals fate in multiple ways. A light star lives a long, long time. A medium mass star lives a medium amount of time. A big, massive star lives a very short time in comparison. And so then we go on to death of the star. So this is where stars' lives start looking different. All stars chill out here on the main sequence. All stars, well, yeah, all stars as far as we are concerned chill out here on the main sequence for the majority of their lifetimes. There's Cepheid variable stars. I'm not going to get into those. But we're going to go into the death of the star. So the star has lived in the main sequence, and we're going to start out with a solar mass just like our own sun, 1 solar mass. What happens? Well, it's chilling out on the main sequence for a fairly long time, about 10 billion years, more or less. And then it becomes a red giant, and then a planetary nebula, and then a white dwarf. So we're going to go into each one of those in a little bit more depth. So here we're staying for, again, millions or billions actually of years. In the main sequence, hydrogen starts to run out in the core. And so we start losing some of this nuclear radiation pressure outwards. Gravity begins to win, and the star starts to shrink. The shrinking causes the temperature and pressure to increase. Because again, if you shrink something, like you compress a bunch of air inside of an engine, then that stuff is going to have a higher temperature and a higher pressure. And so that means that we're going to start getting some fusion of heavier elements. And as this happens, the star actually expands. Weird, right? And this causes it to become a red giant. And that's because the nuclear pressure has increased because there's now helium fusion happening within the core. And so this star is expanding. Our sun might expand all the way past Saturn. We're not entirely sure, but it's definitely going to be bad news for us here on Earth. And so the star becomes a red giant. It leaves the main sequence and goes up into the red giant region of the HR diagram. But the thing is, eventually the core runs out of helium. And when that happens, the star becomes a planetary nebula. And what this is the star has expanded outwards so far that once the nuclear pressure sort of decreases, gravity starts to win and sort of pull the star back in. But the outer layers have gotten so far away that they start to sort of poof away from the star, or blow away from the star. And that's usually the radiative zone, the outer edge of the star, not the core area. And so these outer layers blow away and start to sort of move away from the star, and do so in kind of a spherical way, because again, the star is spherical, so it makes sense that that's going to be spherical looking. So these are some really lovely pictures. They're called planetary nebulas because astronomers thought they looked like planets. Again, they're not planets, they're stars, corpses. Yeah, that's morbid. But they're really, really pretty. This is the Cat's Eye Nebula. Ooh, this might be the ring, but it's a weird picture, so I might be wrong. It might be the Helix Nebula, the Hourglass Nebula. They're very pretty. The inner structure, we're not entirely sure why these different structures form, but that's something that astronomers are actually currently studying. So the exterior of the star sort of poofs away from it, and then the interior of the star doesn't have any radiation pressure remaining because it's not fusing anymore, so we don't have any of those really high energy photons pushing outwards, causing the star to be in equilibrium. And so it becomes a white dwarf. And this is for stars that start out 8 to 10 times the mass of our sun. But the key is that the leftover core of the star that hasn't poofed away and become a planetary nebula is less than 1.4 times the mass of the sun. So the leftover core chunk is under, it's called the Chandrasekhar limit, 1.4 times the mass of the sun, becomes a white dwarf. So under this size limit, the remaining star is a white dwarf. You can just barely see the white dwarf right here in the Ring Nebula. It's pretty hard to see, but it's there. And a white dwarf is just hot and small and dense, and it has a pretty low luminosity. So they are down here on the HR diagram, and they're pretty boring. They're just going to gradually glow. So again, that glow is the black body radiation because of the temperature of that star. And as it glows, it's actually releasing that energy into space as photons. And eventually it'll lose that energy and it dies as a black dwarf, as a rock that's not radiating energy. It's not going to collapse any further due to gravity because as all of these particles are pulled closer and closer together, we get something called the electron degeneracy pressure, which is caused by something called the de Pauli exclusion. Anyway, it's the best way to think about it is you remember from chemistry that like electrons hang out in specific locations around the atom, and they have to be in those specific locations, and they can't be like halfway between them. So electron degeneracy is that electrons have specific seats that they can exist in, and they can't share them. So you can't have two electrons in the same spin, in the same orbital. It's impossible. It won't work. And so that means that those electrons need to be in two different orbitals, which means they need to take up a little bit more space. And so because of this, we get something called the electron degeneracy pressure, which is electrons pushing outwards. So instead of the star having a balance of radiation pressure and gravity to make it stable, it has electron degeneracy pressure and gravity that's making it be stable. And that's for this white dwarf. And that electron degeneracy pressure will still be there even when it is a black dwarf. And then it's not actually technically a rock. It would still be a gas, I think. Well, that's an interesting question. I'll think about that more. So that was for a star very much like our own sun. Then we're going to talk about these high mass stars. And high mass stars, again, hang out in the main sequence. They're not there quite as long as our sun is. And then they become red supergiants, supernovas, and finally, either a black hole or a neutron star. And we'll talk about what that decision, like which one it becomes, specifically. But now I need to start a new video recording because my video is too long.